Consider the following functions. We have f of x equals 3x minus 7 and g of x equals 2 minus x. Our first composition, the composition of f and g of x, in other notation you can write that as f composed of g of x. What we're going to do in this particular composition is we're going to take function g and substitute it into the variable of function f. So this is going to become f of 2 minus x, because that's what g of x is defined as. When you go to function f, the only place to substitute is behind the 3. So 3 times 2 minus x minus 7. That's 6 minus 3x minus 7. Combining like terms is negative 3x minus 1. Your compositions can be written in various forms. At the top right, we have the composition of g and f of x. So that's going to be g of f of x. F of x is defined as 3x minus 7. G of 3x minus 7, we're going to plug that in right here. 2 minus 3x minus 7. Distribute your negative 2 minus 3x plus 7. Combining like terms, negative 3x plus 9. We also have a composition of g with itself. So that's g, open circle g, of x. So we're going to take the function g and substitute it into itself. It's a weird notation. Concentrate up here at your top, 2 minus x. We're going to take 2 minus x and substitute it into that little variable. G of 2 minus x is 2 minus 2 minus x. Distribute your negative. 2 minus 2 plus x. 2 minus 2 cancels out to 0, so all we're left with is x. In this follow-up example, we have two fresh functions. Function f is defined as the cube root of x minus 2. Function g is defined as x cubed plus 2. The composition of f and g of x is where we take function g, substitute it into the variable. If there's more than one variable, you substitute it into everywhere there's a variable. But we only have one variable here. X cubed plus 2, that's going to go into this variable position, giving us cube root of x cubed plus 2 minus 2. The 2's zero out. We're left with cube root of x cubed, which is x to the first. 3 divided by 3, x to the first. If the composition is written g circle f of x, then we're going to take function f, which is this cube root function, and we're going to substitute it right in here to the variable of g. That becomes cube root of x minus 2 cubed plus 2. The cube root and the cube cancel one another, leaving x minus 2 plus 2. Those zero out, leaving x. It turns out, and we're going to discuss that in a little bit, if the composition done both ways equals x, then these two functions are inverses of one another. They do the opposite operations in reverse order. Back to the composition of g with itself of x, we're going to take function g, x cubed plus 2, and we're going to substitute that right in here with that x. So that becomes x cubed plus 2, quantity cubed plus 2. If you wanted to expand this, you would write 3 x cubed plus 2's, multiply them all out, and then add 2 to your constant at the very end. I didn't require y'all to do that in class. My biggest focus is you being able to get the correct substitutions made. Verify that the functions are inverses algebraically and then graphically. Let's focus on the two functions given. We have 2x minus 4. That's our f of x function. G of x is defined as x plus 4 over 2. If you were to split these terms up using 2 as a common denominator, you would get 1/2 x plus 2. That'll actually help us when we get ready to do the graphing. As far as algebraically verifying, you do your composition in both directions. So we're going to do the composition of f and g, the composition of g with f, and then if both of those come out to x, we have verified that those are inverses. This first composition, we take function g, so x plus 4 over 2, and we sub that into the variable of f. That's 2 times x plus 4 over 2 minus 4. The 2's cancel. X plus 4 minus 4. The 4's cancel, leaving us x. Let's check the other composition. This time we're going to take 2x minus 4 and substitute it in for this x. 2x minus 4 plus 4 over 2. Our 4's zero out. 2x over 2. The 2's cancel, leaving x. Both compositions equal x. Function f is a line with slope 2 and a y-intercept of -4. That is this line over to the right side of your screen. Y-intercept -4, slope of +2. The other function is a line that has a slope of 1/2 and a y-intercept of +2. That is this function, and I've labeled them f and g so that you can see them. It turns out for inverse functions, if I pick a point like, let's go back to function f. I know that -0, -4 is a point on it because that's the y-intercept. If you reverse that point, you get -4, 0. That's a point on the inverse. Let's take another point, 1, -2, and I can find that because I know the slope is 2. If I go up 2 over 1, I land back on the line. So this point has the coordinate 1, -2. If I reverse that, -2, 1, I find that point on the inverse. And that's true for all points on one function. If you reverse or transpose the coordinate, you will have a fresh point that lies on the inverse. Y equals x is the mirror for one function onto its inverse. The next example, we have f of x defined as square root of x plus 3, and g of x defined as x squared minus 3, but only when x is greater than or equal to 0. I'll explain that in just a moment. First, let's verify that these are inverses algebraically. Let's start with the first composition, f composed of g. We're going to take function g, substitute it into function f. So x squared minus 3 will go right here, giving us square root of x squared minus 3 plus 3. The 3's cancel. Square root of x squared is x. Technically, it's absolute value of x, but we're not going to worry about that. We just needed to make sure that x was our answer. Now, if our answer isn't x, you just stop here. You don't even have to do the other composition. But since it is x, we go forward. G composed of f of x, we're going to take function f and substitute it in here. Square root of x plus 3 goes right here. That means we're going to square it, subtract 3, square root and square cancel. X plus 3 minus 3 is x. We get x again. Since both compositions equal x, we have verified that these two functions are inverses. Okay, now function f, we have to be very careful here. The square root of x plus 3, this is doable as long as we have 0 or a positive. The smallest value of x that we can use is -3, because -3 plus 3 is 0, and that's the closest you can get to the negatives without being negative. Square root of 0 is 0. So that tells us our starting point is -3, 0. Over here, the graph in pink is going to be f of x. Our starting point is -3, 0. Picking another value of x that will work, suppose I take x equal to 1. 1 plus 3 is 4, square root of 4 is 2. If I plug in a 1 and my answer is 2, then that means 1, 2 is a point on that graph. And if you do that a little bit more and you generate more points, for example, if x is 6, 6 plus 3 is 9, square root of 9 is 3, that tells me that 6, 3 is a point on this graph. This pink graph represents the connection of all ordered pairs for function f. Function g is a quadratic function. Quadratic functions with a positive x squared term look like valleys. Now we know from our previous sections that this graph should be more than what we see, and that's true. That's a valley. But in order for g to be 1-to-1, which means each unique x has a unique y paired up with it, we can only use half of the parabola. And that's why we have this stipulation of x greater than or equal to 0, is because only the right half of this parabola is 1-to-1, meaning unique x equals a unique y. You never have a repetition of an x or a y. Let's note that we're told that x has to start at 0, so 0 subbed in, that gives us -3, 0, -3 is the starting point for this parabola. All right, so let's go back to the pink graph. We started with -3, 0, and if you transpose or reverse those, you get 0, -3. We also found the point 1, 2. If I reverse that, I get 2, 1. That point is on the inverse function. We also found 6, 3 on function f. If you plug in a 6, your answer's 3. If I reverse that, where do I get? That's right, 3, 6. So 6, 3 reversed gives you 3, 6. And you sketch a parabola through those points, and that is a visual connection of all ordered pairs that satisfies function g. I lightly scratched in y equals x. That's the line that would connect all points with the same x and y coordinate. That is the mirror reflection from a function to its inverse. The pink graph, since its x values are limited to -3 and larger, its domain is -3 to infinity. The y values on the graph, the lowest one or smallest is 0. The y values go up as you go right, so the range is 0 to infinity. Switching over to the parabola g of x, the first x coordinate that it's defined for is 0. X values can get larger, and they go all the way to infinity. The range is a set of y values covered by the function. At this lowest point, the y value is -3. The y values only get larger from there, so we go to infinity. Note the domain and range for one function and its inverses also, or in its inverse, also swap out. So not only can you swap the order of coordinates from point to point, you also swap your domain and range.